Okay, so hi everyone. I'm Akshara and I'm going to be running through the 1701 crash course today. I did this course in 2022 and it's changed quite a bit since then, or 2021 actually. Um, so there used to be a statistics component, which was the second half of the course. Basically, they've removed all of that and they've just made it solely about environmental principles and concepts, which is really great because we often don't get to learn those concepts in any of the other courses. Um, the new parts of the course are the climate change management aspects, which you guys will be learning about really soon, actually. So, weeks 1, 2, and 3, and then you'll have your quiz one at the end of that week. So, unfortunately, I won't be able to cover much of those topics there. However, I will go through the majority of the second half of the course, which will be your sustainability principles and your environmental concepts. So, mainly today, I will be going through environmental sustainability part one, which kind of focuses on sustainability terms and principles and doing our best to basically define the term sustainability, which makes it really easy to apply to development and kind of measure the success or the sustainability of a project. So some important terms that you'll learn in that part of the course will be industrial ecology and circular economy, which I'll go through a lot in this crash course, just because it will come back a lot in your future courses as well. I will also touch a little bit on material flow analysis. That's quite a common exam question, and they're kind of easy marks if you know the method. There's usually only one method, so I'll go through an example with you later on in the crash course. And I will also be going through some of the carbon accounting and environmental footprint notes, because that's a really huge part of your first assignment, where you'll be, I guess, quantitatively measuring the carbon footprint of, a project, a site, even an individual. Right. So, by the way, this table that you see here is from your course outline, so the 2024 course outline, so all relevant to you. Basically, just to give you a brief overview of the course, you're going to be studying the science behind global change and basically how we can use sustainability to measure the success of any kind of development. So, when you're working on a project, usually how the industry measures success is, through the cost analysis, how efficient the project is, how much time it takes to, I guess, set up the development or the site. But sustainability should be a criteria too. And this course is basically all about how the New South Wales government has put in regulations so that any kind of development that occurs in the state and across the country uses sustainability as a criteria to ensure that we're minimizing our environmental impact. So another thing to remember is any definitions that you'll come across in this course are really likely to come back in second, third, and fourth year courses. So in CVEN1701, which is Environmental Frameworks, Law and Economics, a lot of these terms will just be assumed knowledge. Also in a course called 3702, which I'm currently completing now, some of the terms are brought back in regard to waste management. So all of these terms are really important just to remember for the future. Okay, so enough about that. I'll just get started, I guess. So I'll just give you a brief introduction to some terms that are going to be really common throughout the course. So when you think about environmental impacts, there will be a couple of terms that are thrown around. Most of them you've heard before: pollution, waste, but it could also be threats to the environment, such as energy consumption, global warming, you've definitely heard of. The impacts could affect biodiversity levels, and ecotoxicity is also a threat to ecosystems in Australia specifically. One thing that will keep coming up throughout the course is um, you'll keep being asked to apply these sustainability principles to the environment in Australia. So, in your lecture slides, there'll be a lot about the state of the Australian environments in particular, and why it's really important to be conserving those ecosystems, just because there aren't any others like it in the rest of the world. But yeah, biodiversity specifically is really important in that regard, just because our biodiversity is very unique. Okay, planetary boundaries. So this is a term to kind of describe the limits of the natural resources in our planet. So climate change, the way that our land is changing, the amount of fresh water that is available to us, all of those are limits because the natural resources on Earth are finite, which is a word that you'll keep hearing throughout the course as well. The whole point of sustainability is that we should be able to keep using these natural resources long into the future. However, if we exceed planetary boundaries, then we're less likely to be able to do that. So whether a project is impacting planetary boundaries too much is a way to measure whether the course or like the course of the project needs to be like altered or anything. IPAT is a quantitative way to measure the environmental impact of a project. So just environmental impact, population, affluence, which is the consumption per capita, and technology. All of those factors play a part in the value of a country's impact, a person's impact, the impact of a project. And it all comes down to how many people are contributing to the impact itself, the economic unit being used, and then the impact in terms of whether planetary bounds have been exceeded or what type the impacts are as well. So that's something that could be thrown into one of your quizzes. It's kind of a relatively easy equation to remember, so just keep that one in mind. I'll skip down to here. So probably more than any other word in the course, sustainability is the one that you'll hear the most often. And it's a very broad term, so I decided to kind of divide it up into 4 sections of 4 contexts that you'll hear about in the course. So one thing that you will hear over and over again is that the definition of sustainability is always changing, but one constant is that it means, or it's a way to measure the capacity to continue something for an indefinite period. So let's say I'm building a wastewater plant on a particular site. The sustainability of that wastewater plant will depend on how long I'm going to be able to use it and how long I'm going to be able to operate it without causing detrimental impacts on the surrounding environment. So you'll hear things like endurance capacity. Like I said before, a lot will be based on the fact that the natural resources are finite and can't be consumed at too high of a rate. So that's the definition of sustainability. Number 2 is kind of the ideas behind sustainability. So the reasons why we need to consider it basically is because, like I said before, natural resources, economic resources, and our social and institutional systems are all finite. And those are all things that human development rely on. So if we one day run out of natural resources or economic resources, human development is hindered. So in order for us to be able to continue with that sustainably, we kind of have to design processes that have sustainability in mind. Number 3 is the sustainable approach. This diagram here is probably one of the most important diagrams in the whole course, as simple as it is. So it's basically representative of the circular economy, which I will go into a bit more detail about later. So the idea is that because the environment determines so many of our resources mentioned here, social and economic approaches to projects, or social and economic aspects of a project, should all come under the environmental aspects of that project. So they should all consider the impact that they're having on the environment itself, which will allow us to figure out how long we're going to be able to continue the approach of whatever development you're working on. But again, I'll go into a bit more detail about that later. And then number 4, very quickly, I will just mention a couple of things that you've probably already heard. Threats to sustainability is the last thing that you'll probably hear more than any other concept in this course. So overconsumption and overproduction obviously are huge. Rapidly growing population. So even though our development has a huge impact on the environment, it's not as if we can stop it. We have to meet the demand for infrastructure due to the rapidly growing population. So what you'll often have to discuss is how you can continue to meet the demand of a rapidly growing population, urbanization, and how you're able to sustain that level of development without hindering the environment as much. Okay, so that was sustainability basically in a nutshell. There's probably a lot more that your lecturer will go through in a lot more detail, but as long as you keep referencing those 4 aspects of sustainability, I think you can basically attack any written response quite well. Okay, so we'll delve a little bit more into the more important terms now. So like I mentioned before in your course outline, industrial ecology and circular economy are 2 huge parts of the content that you'll be assessed on in quiz 2. So we'll spend a little bit of time defining each one just because you might not have heard them before. So industrial ecology is basically the study of your industrial systems and their impacts on ecology and the ecosystems that are natural. It also considers the natural systems, I guess, as like a template for design. So we should be able to study a natural system and kind of mimic the way that it works in terms of our industrial systems. One of the big concepts in that area is that natural systems don't technically have any waste, so everything serves a purpose, and nothing is without its, nothing is without its purpose, essentially. So that's what we call life cycle thinking. So at all points in a life cycle, an organism or an environment is serving the next stage. So the whole point of industrial ecology is that we use that idea of a life cycle and we kind of apply it to an industrial development so that we limit the amount of waste that is produced. 2 important words here are resources and sinks. So resources you've definitely heard before. That's anything that we extract or use for development. You'll have your natural resources, your economic resources, And then your sinks are what we're, putting those resources to. So your sink will be your development or your city or your population, essentially. And they're the things that are absorbing and taking in the waste products. So in terms of sinks, you want to be imposing the least amount of waste possible. Okay, we'll keep moving. Yep. So I mentioned before that circular economy was a really important concept that you'll keep hearing. The reason why we're trying to avoid linear economy is because of what I mentioned before about minimizing waste. So with linear approaches, you'll have your process beginning and then your ending, and whatever happens in between, you'll have a fixed set amount of waste at the end. But the idea of circular economy is that you won't have any, useless waste at the end. It'll keep, benefiting the next stage of the process, which intuitively is much more sustainable than a linear approach. So, things like eliminating waste, circulating products and materials, and I guess copying the idea that in nature or in natural systems there are no waste stages for us to get rid of. There's no landfill, there's no diverting waste. Everything serves the next stage of the process, which is basically what this diagram is all about here. So I'll just put that diagram. Oh yeah, you can see it. Okay, so as you can see here, you'll see a lot of diagrams similar to this, like this, in your lecture slides. I'm pretty sure this was taken from one of mine as well. But the idea is that at any point during the development process or during the project lifecycle, your project outputs are serving the next stage of the process. So here, the use is controlled by the buyer, owner, consumers of goods, or by fleet managers who retain ownership and sell goods as services. So once that stage is finished and the waste products are produced, they're either recycled and moved on to the manufacturing process, which is probably what most people would think as the beginning stage, I guess. So once those materials are recycled, they're basically brought back to the beginning, and they can be made into new goods, or they can be reused, or they can be converted into an entirely different, or their use can be converted to an entirely different one. And then, distribution from that point onwards, and then we're back at the use of that product. So at no point are we diverting the waste products to landfill for them to create pollutants and impact the environment. Every waste product is, I guess, brought into a new stage. Okay, so this is a closer look at the recycling concept. So I know you've heard about recycling before, but in this course you'll have a look at recycling as more of like a cycle in itself. So once the product has been used and the materials, are no longer or can no longer be used for their intended purpose, the idea is that we want to recycle them. But recycling itself requires energy and material input, and it requires its own plants, its own processes, which in turn output lots of waste and emissions and degraded materials. So whilst recycling is a better alternative to just diverting the waste to landfill, we still have to consider that recycling has its own impact on the environment. So we need to consider where the energy and the materials that need to be inputted into the recycling plant are coming from. And we also need to consider the waste and the emissions, or rather the volume of waste and emissions that are coming out of the recycling process. So yeah, a lot of the processes that you'll learn about in this course, you'll keep hearing the terms like outputs and inputs. And the way that we measure the success of a process is if the outputs are less damaging to the environment and can be used in another stage or can be used for another purpose. If we're just diverting the outputs to landfill and we're not using the waste in any way, it's just going to continue impacting the environment no matter what the original process is for. So even if we are recycling our original waste, so basically the primary materials that are being used, if we don't consider the impact of the actual recycling process itself, then the environmental impact is still going to be quite great. Okay, so that was just kind of an overview of sustainability and circular economy. Hopefully you guys understood that. I'll keep going now down to these diagrams. So I just wanted to throw these in here just because in your lecture slides will be a lot of different figures. It's not so much like definitions. Obviously there are a few that you'll have to remember, but a lot of this course is like reading figures and recognizing where the terms need to be applied. And it's about studying data and figuring out how to alter a process if it's going to be damaging to the environment. So I'll just give you a little introduction to some of the more important figures. So the waste hierarchy is something that you will have to talk about a lot in your first assignment. And basically, well, you can kind of see it on this diagram here, but the ways in which we deal with waste, there's a hierarchy to which ones we prefer. So down here we have disposal. So at all costs, we want to avoid diverting waste to landfill. We don't want to be doing that because that serves no purpose. It just impacts the environment. There's no benefits whatsoever, except for maybe it might be cheaper. But like we said before, cost can't be the only criteria in measuring the success of a project. In this course, we're trying to think about how sustainability should be used as a criteria instead. And so disposal is not ideal in terms of the waste hierarchy. So next we've got treat, recover, and recycle. So you'll notice that recycle isn't actually that high on the hierarchy just because of what I mentioned before. Recycling plants are their own or have their own impact on the environment, and so does recovery and like wastewater treatment, for example. They all have their own emissions and impacts on the environment, and so we would much rather, go for processes like this, even though these are the ones that we would go for over disposal. So in the most preferable, we just want to avoid waste altogether. And the only way to do that is by taking on a circular approach, where at every stage, the products or the outputs are benefiting the next stage, and then, so on and so forth. Over here is a bit more of a complicated overview of just exactly the same thing. So in the top tier here, refuse, rethink, it's the same thing as avoid. Reducing the amount of waste that we produce. So maybe, for example, in a wastewater plant, your processes are outputting chemicals like methane and carbon dioxide. Methane can be used in the production of energy. So whilst the carbon dioxide is obviously going to contribute to global warming, and that's not good, you're still reducing the amount of waste that you would have had if you had just disposed of the waste and diverted it to landfill. Prolonging the lifespan of parts and products, that's your middle tier here. So that is where repurposing your waste comes into handy, reusing things for an alternative purpose. So I guess the alternative to a circular approach is basically using whatever your output is and changing the way that it's used. Repairing the product so that you can use it again. All of those things prolong the life cycle, I guess, and will, again, limit the amount of waste that is produced. So here's a bit of a comparison of the 3 kinds of approaches when it comes to waste management. So, like we said, linear approaches, there's no real benefit to the disposal or the waste products if you're using a linear approach. You start with some materials and you end with the same products, and those same products will impose the exact same impact on the environment every time. You're not using or repurposing them in any other way. You're just disposing of the products and they're being diverted to landfill. The recycling economy, it is preferable to linear approaches just because in this case, you can see how including recycling in this part of the project has prolonged the lifespan of the materials. So when the materials go in and, through the production stage and after they're used, some of them are being reused as opposed to being disposed of. But again, even though it reduces the volume of waste produced after one cycle, you still end up with those harmful byproducts of the recycling process. And then here is the circular economy approach. So like what I said before about mimicking the life cycle system or mimicking the natural systems, there's no waste products. So at any point, you're going to have outputs, right? But those outputs aren't being disposed, they're just being used for a different stage of the project. Okay. Over here is kind of where sustainability and everything that I've talked about kind of fits into the assessment or the measure of success. So at the beginning of the crash course, I mentioned how the automatic measure for success is kind of economic or social. So it could be community, community preferences, and it could be how pleased the users are with the development. And then economy, that would be basically how cost effective the process is. But if you don't consider environment in your measure of success, then it's not a sustainable assessment, right? So life cycle assessment thinking, environmental footprint, material flow analysis, I'll go into a little bit more detail later, but this is just a show of how many things need to be considered in partnership with things that are currently considered now. Okay. Before I move on, this is just a bit of a repeat over what I just talked about, so I won't go into any of that right now. What I'm going to do is that I'm going to go back to your course outline and we'll talk a little bit about carbon footprint before we go on to material flow analysis. So like I said at the beginning, carbon accounting and environmental footprints, that's kind of what your assignment 1 is all about. So I will briefly go through it here. So these are my lecture slides from when I did the course. I just decided that these were set out quite nicely, so I wanted to go through them with you. All of these figures you'll be shown in class, so don't worry too much about them. Like I said, you'll be shown a lot of figures in class, and so you don't have to remember all of them, just kind of remember how to read them, I guess. But carbon footprint is what we're going to go through now. So with carbon footprint, what you'll be measuring is the total greenhouse gas emissions caused by any one of these components. So it could be an event, a person, a product, or an organization. But as you probably know, there are many greenhouse gases, right? So what carbon footprint is basically taking all of those greenhouse gases and kind of just pretending that they're all CO2. And basically that gives us a way to quantitatively measure how much greenhouse gases are being emitted by these areas here, right? So it's like when you're doing a problem and you have to convert all the units to be equal. Like you can't add meters and centimeters and kilometers together. That wouldn't make sense. You have to convert all of them to one unit. And that's essentially what we're doing here. You can't add like carbon dioxide and nitrogen and methane and get or perform a fair test. So what we're doing is that we're converting all of it to carbon dioxide and using that unit to determine how high the greenhouse gas emissions are. So it's called carbon dioxide equivalent, and there's a way to calculate and convert to that unit. So yeah, basically what I just said here is explained on the slides as well. So it's a unit that expresses the expected warming impacts of different gases on a common basis, right? So common basis being the key term there. And reference substance as well. That's probably a good way to explain it. This table here is really important. So like I mentioned before, you've got many greenhouse gases here. All of them contribute to the carbon footprint once you convert them to carbon dioxide equivalent. The way to do that is by multiplying the GWP factor, which will basically be multiplied by the molar mass, and then you'll get your carbon dioxide equivalent. So here's your example. The carbon dioxide equivalent of carbon dioxide is just 1, right? Because they're the same thing. But when you've got a different gas is when it, when it changes. So here, if we go up to the table, methane is 28, the GWP is 28. So that's the conversion factor. You multiply 28 by the molar mass of the greenhouse gas, and then you've got your equivalent factor. Okay. So hopefully I explained that well. Let's keep going. Okay. This part, probably more than any other part in the carbon footprint section, is what will be most relevant to your assignment. So in terms of carbon dioxide emissions or greenhouse gas emissions, there are different types, and they're all categorized into different scopes. So I don't have to explain it too much. You can kind of just see here the emissions that are emitted directly from a site. So let's use UNSW as an example. Emissions directly from the uni are scope 1 emissions. So things like maybe our electricity output, let's say there was production happening on site somewhere, so emissions from there, they're all scope 1 emissions. Scope 2 emissions, so anything that is purchased, any utilities that are indirectly related to the emissions on site, that's your scope 2. And then scope 3 is, I guess, even more indirect than scope 2, but still related to the studied site. So a scope 3 emission for UNSW might be, I guess, the travel emissions. Everybody's coming into uni for the, employment, for studying, for whatever. And so those travel emissions are all related to UNSW, but they're scope 3. Right? And so basically in your assignment, what you'll need to do is that you'll probably have to measure the emissions of a site, and you'll have to categorize those, and you'll have to justify why, emission A is a scope 1 emission and emission B is a scope 2 emission. Yeah, you can kind of give this a bit of a read. It's just some definitions for you, everything I just explained about the 3 categories. And yeah, that is kind of all that I will go through for now. About carbon footprint, that's all you really need to know for the assignment as well. So we'll go back to your course outline now. Okay, so now we've covered the sustainability terms. We've also covered carbon footprint and how to measure carbon footprint as well. Now the last thing that I'll do is go into material flow analysis. So I'll do that by going through an example basically. I'm gonna scroll all the way down. By the way, these notes, they'll be provided for you after the crash course. So if anything that I said, didn't make sense or whatever, feel free to refer to them. Okay, material flow analysis. Again, this was taught in week 4 when I did it, so don't pay attention to that. It might not be when this topic is delivered for you guys. But material flow analysis is basically a study of how the materials are moving throughout a process in terms of the space that they're taking up and the time that they're taking to get from point A to point B. So in terms of environmental engineers, an example could be water balance in regions. And then sustainability engineers, which everyone is the circular economy as an example. So basically how the materials are moving from one stage in the circular approach to another. Okay, just some terms that I won't go over very deeply. Anthroposphere. Anytime you see anthro in front of a word, so Anthropocene is another term that you'll hear. It's anything included in like human impact. So anywhere where humans have had like some kind of contribution is considered under the anthroposphere. Just like the biosphere considers everything that is living, and the geosphere considers any like rocks or earth material. Yeah, that's just a term that you'll hear throughout the course. These are quite self-explanatory. So substance, any chemical element or compound. A good is something that will have economic value, and the importance of a good will be determined by whether it's got a positive or a negative economic value. If they have no economic value, that could be something like air or rain, anything that any resource that is natural. Material can be either a substance or a good. So if it's a material, that is not inclusive of anything, I guess, natural. So it's physically, chemically modified substances that are exchanged. And then, yeah, process, stock, flow. You'll hear all of these terms in your lectures as well. But that's a quick overview of the material flow terms. The example that I wanted to go through is here. So at first glance, this is kind of a complicated looking diagram. However, all that it's showing is basically a more complex version of what we saw in the diagrams above. So here's your first stage where the raw materials are being put through the fertilizer. In this case, they've been quantified, so it's a 489.4 value, and that's your input, right? And anything that is inputted into a process or a plant has to be outputted. In the case of material flow analysis, we're studying how exactly those inputs are distributed across the process, and the volume that will be outputted and then probably disposed or brought back to the beginning to be an input again if we're using a circular approach. So I'll go back to the example. The whole idea, it's a bit hard to see, but like the whole idea of this example is that we're supposed to find the value of each of those letters there, right? So those are different points in the process where the materials will have their own value, and our job was to find the value of each letter. And the way that we do that is taking the inputs and minusing the outputs. So in the case of part A here, I took my input, which was 489.4, and I just looked at the diagram, which was the fertilizer, which is the most relevant. There's no other inputs going into the fertilizer, it's just the raw materials. And I know that from the diagram, so ignore the 201.5. What was given to us in the question was 227.4 of the 489.4 was being moved to agricultural purposes. 38.4 was being moved to fertilizer exports, and then 22.4, that could be your waste product, right? So all of those outputs were combined, summed, and taken away from the initial input, which gave us a value of 201.5. Okay? We did the same thing for B. With B, which was the non-agricultural soil component, so this time we're actually focusing on a specific stage in the plant. We had an input of 86.2, which was taken from the agricultural soil. We also had an input of 30.2. So what we did was we just had to add those two inputs there to get 32.4. Sorry, that's not correct. Okay, what I wrote there was not correct. Just because we're studying a specific part of the plant, I must have not written the 86.2 there, but we're supposed to be figuring out the amount of material in that part of the plant, so 86.2 should have been considered as well. And then the waste product is 86.2. Oh, sorry, I'm messing this up. Hang on. Okay, sorry, my bad. 86.2 was outputted, which basically negates the 86.2 input. So essentially, the 32.4 is correct because you don't have to consider either one of these stages. Okay, that should be fine. Yep, so it just considers the 30.2 here, and then way down here in the wastewater section, whatever product was outputted from the wastewater plant is being put back into the non-agricultural soil. That's the 2.2 there. That's where that comes from. And then you get a value of 32.4. Okay, hopefully that made sense. The process is repeated throughout, but all you need to remember is just input minus output. That's all it is, no matter what the value is. But yeah, just be careful. It is hard to make a mistake. Even I just, you saw I just got confused as well. So just be really careful with the arrows, especially with a more complicated diagram like that. But that's a really common exam question, so I wanted to go through that with you at the end. Okay, basically, yep, there's another diagram there. Your exam won't be that complicated. That's quite a difficult one. But you may have to study something like this. So your assignment might require you to look at a site. I don't know what's going to be in your assignment given that the course has changed, but something that they might assess you on is basically looking at a diagram like this and maybe not performing a material flow analysis like we did with the first diagram, but basically looking at, let's say, the household sector and kind of comparing how much material is being inputted and outputted in comparison to, let's say, like the surface water unit, right? So here you can see that the output is like 583, 3,454. That's quite a large output. And so you might have to justify why the household sector is outputting so much in comparison to the surface water sector, for example. But that's really all I had for this crash course. So hopefully you understood that. I'll just bring you right back to the course outline here. But yeah, that's all there was. Thank you for sticking around.